Okay, Assalamualaikum and good day everybody. So today I'm going to continue with the damp free vibration and also forced vibration. So now we have learned how to include a damper in our system, our vibrating system. So now we are going to learn how to answer question related to damp system. Either it is free vibration or forced vibration. So the first one, we are going to learn two examples. The first example is related to free vibration with damper, and the second one will be damp forced vibration. So now we go to the first example. So you can see the diagram in this question. We are using example in dynamic book by Shigley, if I'm not mistaken, or Miriam, if I'm not mistaken. So if you have the book, you can refer that. I'm going to use lots of example from the book. So don't worry, I will give you the diagram. Even this diagram is inside the lecture slide. So now we go to the question. We have 8 kilogram body. It's right here, the brown body, and it is moved 0.2 meter to the right. So in x direction, it is moved 0.2 meter. Okay. So it is from the equilibrium position. Therefore, we have stress from the spring and also from the dashboard. All right. And afterward, we release it. We will release it, and it will vibrate continuously. But because we have this condition is free vibration, therefore it will be damped by the damper, and finally it will stop. So the question asks us to determine the displacement equation, and therefore we can calculate the displacement at time t equal to 2 seconds. So it is given that the coefficient of damping is 20 Newton second per meter. That is Newton per velocity, force per velocity, and the spring stiffness is K is 32 Newton per meter. Alright. So first we can draw the free body diagram. If you look at the bottom right, we have the free body diagram. It is good to draw the equilibrium position and also the direction of the x. We can decide the direction. If it is not given, you can decide whether it is to the left hand side or to the right hand side. Each direction is fine, but since it is you can draw also the wall to be at the right hand side or vice versa. So it's fine as long as you got the right direction, you got the right values. So but do not get confused. It's better if you draw according to the given diagram. So we can ignore the vertical component and we just consider the horizontal components, which is the force from the dashboard and the spring. And also we need to consider the kinetic diagram. So in the kinetic diagram we have acceleration positive with the positive direction of x. So acceleration should have similar direction with x. So we combine both free body diagram and kinetic diagram to get the equation. So I'm going to start how to solve this problem. So first we draw the diagram. I'm going to use simple diagram. So we have dashpot and we have spring. Alright, like that. And this is mass. This is coefficient of damping. Alright, so we have. Alright, this is. So we have x direction going to the right. So we are given the constant. M is equal to 8 kilogram. So it's given that at time equal to 0. So we just jot down every information given from the question. So at time equal to 0, we have displacement of 0.2 meter. We have coefficient of damping equal to 20 Newton second per meter. And we have stiffness coefficient. Alright. So now we have done the information given. That's all the information given from the question. So first we need to determine the we need to find the displacement equation. So what we need to do first is, of course, the free body diagram. We just consider the horizontal part. If we have a rotational problem, we need to consider both any angle force involved in the problem. So we have for this free body diagram, we have this force from the dashpot and force from the spring. Or I can write it D, and this is spring S. Alright, so we have mass, and then we consider the kinetic diagram. Kinetic diagram, we only have one component, which is the acceleration. So MA, A is acceleration. So now when we compare both sides, we can know that this equation is it has like the equation I have told you before, x dot c minus k x, alright, equal to mx double dot. Okay, so when we rearrange, we will have mx double dot plus cx dot plus kx equal to 0. So we have homogeneous differential equation because this is free vibration. Alright. So when we have damper, we need to determine what is the damping category, whether it is over damped, critically damped, or under damped. So how to find doubt is by calculating the damping ratio. Okay, so we need to find the zeta. This is zeta. So first we need to find the omega n, natural frequency first. Okay, so omega n is equal to this formula. We know already these values. We just put in these values here. In this case, you don't have to put the unit, but you need to be careful. for example, sometimes the question will write down like this. K is equal to 2.5 K Newton per meter. So in this case, you need to change into like this, Newton per meter. Therefore, you will have no problem in terms of the unit afterward. And we replace M in kilogram. So 8 kilogram. And therefore, you just ignore the the notification above. So we will have that omega n is equal to 2 radian per second. Okay, that's for the natural frequency. Now from here, we can calculate the zeta, the damping ratio. So we just use the formula given previously. So you just put in the value. C is equal to 20. You don't have to put the unit again because to simplify it. So we have M, we know M is 8 kilogram, omega n, natural frequency is equal to 2. Remember, we are using radian, not degree. So if anything is in degree, you need to change into radian. So this one is equal to 0.625. This has no unit, so we can leave it like that. So from here, if zeta is bigger than 1, it is over damped. If zeta is equal to 1, it is critically damped. If zeta is lower than 1, it is under damped. Hopefully you understand. So this is under damped. So then we use the under damped solution. You can go back to the slide. What is the under damped formula that we can use? We have over damped formula, we have critical damped formula, we have under damped formula or solution. So the solution, under damped solution. X, so X is the displacement. C is constant, exponential zeta omega nt sine omega d. So right here we have omega d times t plus psi. So we can denote this as 1. Okay. So in order to know the components, we need to investigate each component. So we found that omega d is unknown. We don't know the value yet, so we need to calculate it. So omega d, we know the formula. Omega d is again the damped natural frequency. So this is the formula, 1 minus zeta. So zeta is useful. So you need to, afterward you need to put the value inside. Again, you don't have to put the unit. It's up to you. If you want to put the unit, also can. So therefore, we get the damped natural frequency equal to 1.561 radian per second. So the unit is still the same, but since we have damper, we have damped natural frequency. Now we put this in 1. So right here. So we get X equal to C exponential negative zeta omega. I think I can put the values straight away. So we multiply zeta with natural frequency, we will get 1.25 t. Okay, t is time, so sine, we have omega d right here, so we put the value 1.561 t plus psi. So we don't know what is psi yet. Okay, so we denote this as 2. Alright, so now we need to find the constant c and psi. Sometimes I need to change color. C and psi. So that is the constant that we need to find. So we need to know the boundary condition. Boundary condition, we know that at t equal to 0, x equal to 0.2. And also at t equal to 0, the velocity is equal to 0. Okay, so now we can put the value right here. So we have 0.2. So we put for the first value right here, we put in equation 2. So we have 0.2 equal to CE. So t is 0. So power of 0. Sine t is equal to 0 again, 0 plus psi. So we can simplify c sine psi, like that. And also we can also rearrange so that c be the subject. So 0.2 over sine psi. Alright. And now we still cannot find the value of c and psi. Don't worry about that. So now we can use another boundary condition. So but before that we need to differentiate. Differentiate equation 2. So we will get x dot equal to so we have the value already, so we can put the, so we can use the multiplication formula for differentiation. So CE negative 1.25 t sine 1.561 t plus psi. And then we plus 1.561 CE negative 1.25 t cos 1.561 t plus psi. Okay, why there is the answer is like this? Because I use the multiplication formula for differentiation. Because we multiply this component, this component with this component. Right. So we get this answer when we differentiate them. Alright. So right now, we can replace x dot equal to 0, t equal to 0. This is t. So 0 is equal to, so we can simplify them. Negative 1.25. We still have c, but e is cancelled because it is equal to 1. Sine psi. plus 1.561 C cos psi. Alright, so this all is equal to 0. Now we still didn't get the answer, the value for C and psi. But don't worry, we can compare with let's say this is number 3 and this is number 4. We can compare 3 and 4. So since we have this one, this is similar like this one. So this is equal to 0.2. Also for C right here, we can replace with this one. So this one is equal to 0.2 sine psi. Alright, so we can elaborate that. So we have negative 2.5 plus 1.561 times 0.2. So we have cos over sine psi. So this one is equal to 1 over tan psi. So now we can rearrange so that we can find the answer for psi. So when we rearrange, we have 2.5 over, so this one is equal to 0.3122 equal to 1 over 10 psi. And after we calculate, we can get that psi is equal to 0.896 radian. So we get the first value, and then we can put this back into number 3 right here. So we can get that C, therefore C is equal to 0.256 meter. And so we get the two constants, the value of them, and then we substitute back to the equation 2. So sub to 2. So x is equal to 0.256 e power of negative 1.25 t sine 1.561 t plus 0.896. Alright, so therefore we get the answer. So this is the displacement equation, the solution for the problem. So this is how the displacement of the vibration behave. So when we continue with the question, it asks what is the displacement when time is equal to 2 seconds. So we just simply put this value inside this equation, and then we can get the x. So to cut short, so x can put it x2 is equal to negative 0.01616 meter. So that's it for the example number 1. Alright, so now we go to the example number 2. So example number 2 is from example 8.6 in the book. I said before this, the dynamic book. So the question is, we have the 45 kilogram piston is supported by a spring of modulus K equal to 35. Now we can see that we have kilonewton for the modulus of the spring stiffness modulus. So we need to change into 35,000 Newton per meter. Therefore, we will not get confused when we do the calculation. We need to change to 35,000 Newton per meter. And dashboard, we have the value for the damping coefficient. We have the fluctuating pressure. Now we are using pressure instead of force. But don't worry. The equation for the pressure is P equal to 4,000 sine 30 T in Pascal. And since we know the top surface area, which is 5 power times 10 power of negative 3 meter square. So from the area, we can multiply with the pressure to get the force, right? So in this question, we need to find the steady state displacement. So you need to understand when it say steady state, it means we consider only the force applied to the system. I mean the vibration caused by the force applied to the system. We can ignore the transient vibration, which is from the free vibration in the system. So that means in the general solution, we can ignore the complementary solution. We just need to include the particular solution or particular integral. Hopefully you understand that. Don't worry, I will show you after this how to do the answer. So we need to determine the steady state displacement. So we just need to find the XP or the particular solution. And then we need to find the maximum force transmitted to the base. So now it's a little different. Not the force transmit to the piston, but to the base. Right. So don't worry about that. We can still calculate that. Right. So we start to do the answer. So example 8.6, we have the piston, we have the mass, we have the pressure from the top. So P is equal to P0 sine omega T. So P also we have the value already given in the question, 4,000 sine 30 T. So this is in Pascal. Alright. So we just jot down every information we get. 45 kilogram. Stiffness is 35 kilonewton. We change to 35,000 Newton per meter. Okay. C is equal to 1250 Newton second per meter. We have the area 5 times 10 power of negative 3 meter square. So now we need to understand what are the question again. We need to find steady state displacement. So for steady state displacement, it means that we need to find the XP. Remember that for the general solution, we have X is equal to X C plus XP. This is complementary solution. This is particular integral or solution. Okay. So we can ignore this one for steady state when the question asks for steady state displacement. Alright. And then this is number 1. Number 2, we need to find maximum force transmitted to base. Now we focus to the first one. Again, whenever we have oh sorry, the diagram is incomplete. We have spring, we have dashboard, and we have base. Alright. So again, it's good practice if you draw the free body diagram and also the kinetic diagram. But I can skip that because I know already. So it's good for you to draw the free body diagram and kinetic diagram. So for the initial step to do the solution is usually we need to find the natural frequency. So for the natural frequency, why we need to find the natural frequency? Because we can get after that the the damping ratio. So we use the formula. Hopefully you already remember this formula. Put the value. See, now make sure that the unit is correct. So we can just put the value alone without the unit, and then we can get the natural frequency. And then for the damping ratio, we use the same formula from previous example. So we just put the value. This is 5. So we have 245 amp is 45 kilogram. We know this already, 27.9, and then we can get the damping ratio. So this is again lower than 1, therefore this is under damped. Okay, or sometimes I write UD only. So now before we continue, we need to understand that this is we need to find the displacement for steady state. So we just use the particular solution. Okay. So the particular solution xp is equal to x. This is the formula for under damped. So sometimes I use sometimes I use C, sometimes I use X. X is the constant that we need to find. Alright. So this is the equation for the steady state, the particular solution. Alright, so I can denote this as 1. So from the lecture note, we know that the amplitude x is equal to, we have the formula for that. So since this is a forced vibration, so the formulation is different compared to free vibration. So this is the formula for the amplitude. It's quite lengthy. Bear with me. Omega over omega n square plus 2 zeta. So actually, if we have damper, this is the formula for the amplitude or for the displacement of particular solution. Okay. But if we don't have damper, the formula is simpler compared to this one. Now we may calculate everything. So to find the F0, F0 is the force, the amplitude of the vibration applied to the piston. So we don't know the force, but we know the pressure. So we can calculate the amplitude of the pressure. We can calculate the force, the amplitude force by from the amplitude pressure. So remember, force is equal to pressure time area. Okay, so the pressure is 4,000 Pascal, the amplitude for the pressure vibration, and we have the area, this value. Okay, so we get the F0, and then we replace the K, 35,000. Right? So, okay, and the bottom one, also replace everything. So the omega is from this equation. So this is the frequency, the omega, and that's not the natural frequency. That's the frequency from applied to the piston. So we just put the value right here, replace the omega, and we know the omega n. We replace it here. Square plus 2. We know the damping ratio 0.497. Again, the omega over omega n, and we square everything. Okay, and we square root everything. We simplify it. We get that the top of the fraction have this value. Okay, and the bottom of the fraction is something like this, 0.0244 plus 1.1424. This is equal to 0.00 again, same, 5714 over 1.08017. And finally we get the amplitude of the displacement, 0.00529 meter. Alright, hopefully you are still with me. So after we get the amplitude, now we can calculate the psi. So for the psi, we have the formula. The phase is phase angle or phase difference. Psi, we have the formula. Psi is equal to tan -1 -1 to zeta omega over omega n 1 minus omega n squared. Right? Again, we just put in the value. We know already every value for each component. To 0.497. So I just write this down quickly. 30 over 27.9. 1 minus 30 over 27.9 squared. And after we calculate it, we can get that. The value is negative. If in radian, we will get negative 1.4257. Since it is impossible to get we call it negative. So we need to find, since this is trigonometry for tan, we will have similar value if we add pi to it. So we can add pi. So this is additional. We can add pi to get the positive value. So after we add pi, we found that the answer is 1.716 radian. So this is the value for psi. Okay, so we get the value of the two constant x and psi already. Now we go back to the equation 1. Equation 1 is right here. So from 1, we can replace the value. Xp is equal to x. I write down again. So this is 0.0000529 sine. We know omega. We know psi. Right? So this is the solution. So this is the displacement. So we answered already the steady state displacement. So number 2, we need to find the maximum force transmit to the base. So number 2. So we need to find force transmit. So if we draw the free body diagram, we have the force from the top, and also we have the force from the bottom. This is kx and this is cx dot from the spring and the dashpot, and therefore we know that the force to the base is similar in different direction, kx and cx dot. Alright? Alright. So we know that FTR is equal to kx p. This is the particular solution plus cx dot, again p. You can ignore the p if you want, and then we can just replace the xp and x dot p. So before that, you need to find the x dot p lah. So this is equal to x dot p is equal to x omega cos omega t minus psi. Okay, so we put this inside here and also this inside here. Okay, we will get that FTR is equal to kx sine omega time minus psi plus c omega x cos omega time minus psi. Right? Okay. Now this is now we go to the tricky part, a little tricky. So this is the force transmitted to the bottom. This is the formula, but we want to know the maximum. So for the maximum, FTR max, it's really we need to understand the trigonometry of this function. Okay, so we can just consider the amplitude. Okay, so without the sine, without the cos, sorry. Amplitude alone. So we are using a Pythagoras theorem. So kx square plus C omega x square, and we can simplify it. We can take out x k square plus c square omega square. Alright, and then we just replace the value again. 35,000 square plus 1250 square 30 square, right? So we will get that the final answer is 18.527 Newton. So this is the maximum force transmitted to the base. So I think that's all. Thank you very much for your attention. Hopefully you understand this. Actually, for the second part, this is sometimes is a little challenging, and it will be the same like this. Sometimes it may be the same, but it can be various kind of question. Actually, you can try other examples in the dynamic book. The dynamic book is Miriam. The author is Miriam, and the title is Dynamic. Okay, and if I'm not mistaken, is in topic 8, or you just search for vibration. So I think that's all for this lecture. Thank you very much. Assalamualaikum. Have a good day.